lot of the last few sessions we've been getting to know the Legendre symbol and doing some example calculations with it. So let me just bring up the board. This was the pages from last week, visualizer pages from last week, when they come up here. Computer's a bit slow today. Just to remind you, we've got our Legendre symbol, n mod p, which takes two values, +1 and -1, +1 where n is a quadratic residue, and -1 where n is a quadratic non-residue. So it's like an indicator function. It's indicating whether or not n is a square under the operation of multiplication modulo p. So the general problem we're faced with is how to evaluate NP. Somebody gives you a huge prime number p, a huge number n, which isn't obviously a square, which isn't a square integer. How the heck do you decide whether that number is a square or not? Now, you could just run through all the possibilities. You could square all the numbers modulo p and see if any of them happen to hit this n, but that's not a very nice way. It's going to be very computationally expensive when p is very large, and it's not very sophisticated. You're just going through all the possibilities and just seeing if n occurs as a square or not. So we'd like a better way to evaluate this. So this is what we did an example of last week. There are a number of key properties which we've already seen about the Legendre symbol, which, when we put them together, give us an algorithm to compute it in general. Okay. So the first property we use is that it's multiplicative. Okay. So our n, we can replace n with its canonical form, its prime factorization, and that immediately gives you the corresponding factorization of the Legendre symbol. So this product sign comes outside, and these exponents come outside. And that's the whole thing justifying that step, is that the Legendre symbol is multiplicative. Okay. So considered as a function on the first argument, and the n here, when you put a product of things here, when you have nm mod p, this is the product of the two Legendre symbols. Okay, so that's just expanding that property gives you this first step here. Now remember, these Legendre symbols are plus or minus. So I'm just quickly reviewing last time. They're either plus or minus 1. So we only need to figure out these for when the exponent alpha I is odd. So that immediately cuts down the work. Because when the exponent alpha I is even, you're automatically going to get +1 when you raise it to the power alpha I, no matter if it was plus or minus 1. So we then just need to examine these for when alpha I is odd. So the problem reduces to this line. And then there's this magical property, which we certainly haven't proved yet, which it's going to take us a few lectures to get to the proof of it. And it's quite a deep result, called the quadratic reciprocity law. So by this stage, the problem has reduced to this kind of problem, evaluating a Legendre symbol PQ, where P and Q are both odd primes. So where P and Q are both odd primes. Well, the quadratic reciprocity law doesn't tell you what the answer is. It doesn't tell you whether it's plus or minus 1, but what it does tell you is how to relate this to QP. Okay. And it's related very, very, very nicely. There's two cases to it. So this is the quadratic reciprocity law. We stated it last week. I'm just reminding you now. PQ is equal to, well, it's equal to minus QP in the special case where both P and Q are congruent to 3 modulo 4. Every odd prime, of course, is congruent to either 1 or 3 modulo 4. Can't be congruent to 0 or 2, because then it's divisible by 2. But in the special case where both the primes are 3 mod 4, then PQ is minus QP. In the other cases, otherwise, PQ has the same value as QP. Either P is a quadratic residue mod Q and Q is a quadratic residue mod P, or they're both non-residues. So this extremely nice relationship there. Okay, so what? You've just replaced one Legendre symbol with another one. Big deal. You're still faced with the same problem, how to evaluate it. But what this does do is, you see, at this stage in the calculation here, the primes in the first position are going to be less than the primes in the second position. But when you flip them around like this, you then have the larger prime in the first position, the smaller one in the second position. So that means then, so if P is less than Q, then you switch from this one to this one. You ask, what's the value of this one? But now the first argument is bigger than the second one. So now this can be replaced by Q prime P. So this is using the congruence property, where Q prime is congruent to Q mod P, and 1 is strictly less than or equal to Q prime is strictly less than P. So we use the smallest positive representative, Q prime, of the congruence class of Q. Now, this Q prime is probably not a prime. So you kind of say, well, so what? You're still faced with the same problem. I started off with a problem, evaluate NP. Now I'm faced with a problem, evaluate, oh, just be careful here. This P isn't the same as that P up there. Yeah, that's a bit misleading. Call that a capital P or something. Anyway, this P is not the same P we started off with. But anyway, we start off with a problem like that. Now you say, well, so what? You're still faced with exactly the same type of problem here. But the point is, the problem we're faced with now is the numbers have gotten smaller, okay? These arguments now are smaller than the arguments we started off with. So they're smaller than the initial ones. And that's the idea of the algorithm. You replace your original problem with a new problem with smaller inputs. And you keep doing that. So you keep going around in a circle. Now you factorize the Q prime. Just look at the ones with the odd exponents, like we did here, and flip them using quadratic reciprocity again. And you'll get a new Legendre symbol, which has even yet smaller arguments. Now, these arguments are always staying positive. They're always staying greater than or equal to 1. And they're getting smaller. So pretty soon, they're going to get very small. They're going to hit the value 2 or 3 or something. So pretty soon, they'll get so small that we can just evaluate them because the arguments are trivial and some known results. In a moment, we're going to settle the question about what the value of 2 mod P is for any P. And later on, we can see what 3 mod P is for any P. So using these properties, we kind of drive the arguments down until they get so small that we're able to evaluate them. So this was the example we did last time. So we started off trying to work out, is 219 a quadratic residue mod 383? Well, who knows? We can't tell just by looking at it. So by going through this process, we factorize 219 into 3 times 73. We flip both of them using quadratic reciprocity. But see, now these smaller primes are now going into the second position. Then using the congruence property, reduce 383 modulo 3 to 2, reduce 383 modulo 73 to 18. Okay, this type of problems here you're faced with, they're of the same type as this problem, evaluate a Legendre symbol, but the arguments are far smaller. Okay. 2, 3, we can just tell by inspection. 2 is not a quadratic residue modulo 3. We know that value. This one we flip using we factorize the 18. 2 by 9, 2 by 3 squared. Do the thing. We don't need to know this value because it's squared. What's 2 mod 73? Well, there's a known result which tells you what the value of 2 mod P is for any prime P. And so you get to the result in far fewer steps than it would have taken to search through all the to kind of manually calculate all the quadratic residues modulo 383 and check whether any of them came out as being 219. So it tells you that 219 is a quadratic residue. What it doesn't tell you is what its square root is. So it's like an existence result. It tells you there is a square root of 219. It doesn't give you any clue as to what it is. Okay. Although, using this factorization idea, because 219 is 3 by 73, if you had the square root of 3 and you had the square root of 73, you multiply them together, then you'd have the square root of 219. But this process in itself doesn't tell you what the square root is going to be. Okay. So a key part of this, well, the algorithm wouldn't work without any of the steps. But the kind of very interesting step for us now, you see, we've proved all the techniques that are involved here, except for the quadratic reciprocity law. There was a slightly longer example we did the other day, still doing the same thing. All of these properties were quite easy to prove except the quadratic reciprocity law, which we haven't proved yet. Okay, it's this very, very clean, very nice relationship between P mod Q and Q mod P. And there's this nice little twist based on the values of P and Q mod 4. I mean, it would have been really, really nice if they were just equal all the time. That would have been that would have made mathematics a hell of a lot easier. And if that were the case, it would probably be the case that we didn't have all these famous unsolved problems in number theory. If PQ was just equal to QP, I don't know, it would signify that the primes behave much more simply than they do. But they don't. There's this little twist based on the quarter of the possibilities. So a quarter of the time, random primes will be, a pair of random primes will both be congruent to 3 mod 4. The other 3/4 of the time, one at least of them will be congruent to 1 mod 4. So PQ will be equal to QP. So this law of quadratic reciprocity is the destination we're working towards at the moment. And it'll take us a few lectures to get there, but get there we will. Okay, so that's kind of we went all through that in detail last week, so it's a quick review. Any questions you'd like to ask me about it now, though, just before we continue on? Anything about this process that you're a little bit unclear about, or yeah? Okay. So the key properties are the multiplicative nature of the Legendre symbol, the fact that you can replace the first number with any other number from the same congruence class, and then key to the whole thing is this law of quadratic reciprocity, which allows you to switch them. And it's that lies behind being able to split the arguments and then use the congruence property. That's what drives the arguments down, reduces them in size until they get so small that their values can just be read off. Okay. So our first step towards proving the quadratic law of quadratic reciprocity is proving something called Euler's criterion, which gives us a neat, on the face of it, it looks like an easy way to calculate n mod p. To calculate n mod p, to calculate the Legendre symbol np, you just simply raise n to the power of p minus 1 over 2, and, well, if we believe the theorem, that will be congruent to plus or minus 1. So you may think, what's the big fuss? Well, why do we need quadratic reciprocity? Why can't we just use that formula? Well, that formula requires you to raise n to the power of p minus 1 over 2. So it requires p minus 1 over 2 multiplications. So it's more or less just as computationally expensive as searching through manually all the squares modulo p and looking for if n ever occurs. So although it looks tempting as a nice, easy formula that you might be able to use to calculate with in practice, it's more or less as expensive computationally as just searching through and calculating manually what all the quadratic residues are. So it's perhaps not useful for raw calculation for large arguments n and p, but it is nice to use as a basis for proving facts about the Legendre symbol. It's a very nice result to have, to which we can build other results on top of it. Okay, so let's think about. There's a proof there in the notes about it, but I think we can. I'll give just an explanation for it, not reading from the notes, just working on the board. So how do you prove this? Well, there's a little bit of a discussion before it launches into the thing. Remember Fermat's little theorem, right? Which told us that, well, if n was an element from Zp from the multiplicative group, i.e. the GCD of n and p was 1, Fermat's little theorem said that n to the power p minus 1 is congruent to 1 mod p. Now, we can take the square root of both sides, because p minus 1 over 2 is an even number. Because remember, in all of this, p is always an odd prime. So you can take the square root of both sides. We can instead raise n to a half of that power p minus 1. That's still an integer. And we know how to take a square root of 1. 1 is always a quadratic residue. It always has two square roots, namely plus, sorry for jumping on you, plus or minus 1 mod p. Yeah, they're always the square roots of 1. Now that's really nice, because look, there is something you do with n which produces plus or minus 1, and the Legendre symbol is something you do with n which produces plus or minus 1. So the question is, are they in fact the same indicator? So this is, if you like, a little indicator function which produces an answer plus or minus 1 on n, but the Legendre symbol is as well. So what this theorem 8.4 is saying is just that they both agree, that they are the same kind of indicator function. So we proved this, well, first assume n is a quadratic residue. And what have I always told you about when you're working with these concepts and you want to start building an argument? If the argument says, well, assume n is a quadratic residue, the very next step is what have I told you to do with these definitions? It's to unravel them, yeah? Like what exactly does that mean when we say n is a quadratic residue? Well, it means there exists some other number m such that n is equal to m squared. Sorry, n is congruent to m squared modulo p, let's say. Right? Well, then you can see straight away that you're going to get plus 1 as expected, because then n to the power p minus 1 over 2 is going to be congruent to m squared to the power p minus 1 over 2, and the 2's cancel. Yeah. This is already a square, so this is congruent to m to the power p minus 1. And Fermat's theorem tells us that that is congruent to 1 modulo p. So the quadratic residues do indeed, when you raise them to the power p minus 1 over 2, do indeed give you 1, plus 1. So that's congruent to NP in this case. So the result is true. This result is true whenever n is a quadratic residue. What about the non-residues? So now we consider n a quadratic non-residue. Now that's a negative property. You can't immediately unravel it and look at that it brings into the existence of another object, m here, which you can base an argument on, because it's saying no such thing exists. So It's normally a different kind of argument that you produce on this. Well, what was I saying? Yeah, how do we do this? Look, what we've observed in the previous line note that previously just here, we found, well, we found solutions to the polynomial congruence. Well, it was n to the power of p minus 1 over 2 congruent to 1. Well, let's just write it as a congruence. We found some solutions to this because they were the quadratic residues. Now, how many solutions did we find to this? How many quadratic residues are there? P minus 1 over 2. So we found solutions, p minus 1 over 2 of them, to this polynomial congruence. Are there any other solutions to this polynomial congruence then? To cast our minds back a few chapters. This is an example of a polynomial congruence. We proved our results. Was it Legendre? Who did we call it? It was either Legendre or the other guy. It was about the degree of polynomial congruences when they're modulo a prime, and that giving you an upper bound on the number of solutions. It's not Legendre, it's the other guy. Lagrange. Lagrange's theorem, which is theorem 8.1, no, 7.1, said that this kind of congruence has at most p minus 1 over 2 solutions. When the congruence was modulo a prime, the degree of the polynomial is an upper bound on the number of solutions. So we've already identified p minus 1 over 2 solutions, so there can be no other ones. Lagrange, not Legendre. I keep getting those two guys confused. Lagrange's theorem, 7.1, these are all the solutions of this. There are no other ones. When n is a quadratic residue, it's a solution of this, and that's all of them. There can't be any other ones. We've already proved that can't be the case. So that was just an observation about what we proved. So now when n is a quadratic non-residue, really I should have said this here. So if n is a non-residue, well, n to the power of p minus 1 over 2, it can't be congruent to plus 1 mod p. So what's the only other option? We've already decided that these things have to be congruent to plus or minus 1. If they can't be congruent to plus 1, it's got to be congruent to minus 1. Simple as. So n to the power of p minus 1 over 2 has to be congruent to minus 1 mod p. That comes from this observation here. Because these are square roots of 1 from Fermat's little theorem. So they have to be congruent to plus 1 or minus 1. So it's congruent to minus 1, and this is indeed the value of the Legendre symbol in this case, because n is a non-residue. So the Legendre symbol, by definition, is minus 1. So that gives us the result. Therefore, this Legendre symbol is congruent to n to the power of p minus 1 over 2 modulo p. Or there's one more little case is when this is 0, like when p divides n, this is defined to be 0. But of course, if p divides n, then n is 0 mod p, so 0 to any power is still going to be 0 mod p. So, yeah. These are the interesting cases when n is a residue and n is a non-residue. So this result is called Euler's criterion. So as I said, it looks on the face of it great. We can now calculate what we can now figure out whether any given number is a quadratic residue. Well, yeah, but it's still computationally expensive. It still requires p minus 1 over 2 multiplications, or p minus 1 over 2 minus 1 multiplications, whatever, to figure out this power. So it's no better really than just going through all the quadratic, all the first half of the quadratic, all the first half of the congruence classes mod p and squaring them and then finding the quadratic residues that way. So it's not a computational improvement on what just working off the definition. But it is a conceptual improvement. We do have a really nice way of thinking about the Legendre symbol now. It's just a power of n. We can build arguments on that. So I'd like to get through, well, I'll take any questions on this now, but I'd like to get through the next two results, which are looking at some of the special values. I hope I got the recording going. Yeah, looking at some special values of the Legendre symbol, namely what its values are on -1 and 2. Okay. But any questions at the moment on that? Is that okay? I just want to take a picture of that. I'll stick it up on the board afterwards. Right. Okay, so our next two results, theorem 8.5 and 8.6. So these are special values of the Legendre symbol. So what I mean by special values? Well, these are the kind of results which we're going to invoke. Remember the example I showed you when we started off today that we did last week? I just reminded you of when we have this chain of equalities between different Legendre symbols. We're driving the arguments down. So eventually we're going to reach small arguments. And the claim is small arguments we'll know the value of. So here's Euler's criterion. Just put that up here to remind us. So now we're going to settle what -1 is. Is -1 a square modulo p? So another way to think about this is also p minus 1 mod p. -1 is congruent to p minus 1. Well, you can see it's a really nice result. But we can just discover it. It's just a simple application of Euler's criterion. Okay? So by Euler's criterion, -1p, it's just congruent to -1 to the p minus 1 over 2. Now that's really nice. Powers of -1 are easy to work out, aren't they? How do you work out what a power of -1 is? It's +1 or -1, isn't it? Just depending on whether the power is odd or even. So this is equal to +1 when p minus 1 over 2 is even, and -1 when p minus 1 over 2 is odd. Yeah? Powers of -1 are very easy to understand. +1 or -1. Now you could just leave the result like that, or p, remember, is an odd prime. So p is an odd number. P minus 1 over 2. So p is an odd number. P minus 1 will always be an even number. So you can always divide it by 2. You get another integer. So what is it? We just want a nice way to record the fact, or just express the fact of when p minus 1 over 2 is even and when p minus 1 over 2 is odd. If you just start looking at the odd numbers, 3, 5, 7, 9, 11, 13, 15, 17. What's p minus 1 over 2? P minus 1 over 2 is 1. P minus 1 over 2 is 2. P minus 1 over 2 is 3. You're starting to spot a pattern here. P minus 1 over 2 is 4. P minus 1 over 2 is 5. Da, 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 da. Those numbers that every second odd number gives you an odd P minus 1 over 2. Every other second odd number gives you an even P minus 1 over 2. So it's just all the odd numbers just in an alternating way, give you odd, even, odd, even, odd, even for this. Okay? And a nice way to characterize that is just to say, remember, odd numbers modulo 4 are congruent to plus or minus 1 or 1 or 3. So these ones, it's the ones that give you odd are the ones that are congruent to 3 mod 4. Then be 3 itself, 7, 11, so on. They're all congruent to 3 mod 4. The other ones, 5, 9, 13, they're congruent to 1 mod 4. So that's the result. We now know when minus 1 is a quadratic residue modulo P. We know it in terms of the congruence class of P mod 4. So if you're given any prime, you just have to know where it falls in this, whether it's, is it in the first subsequence of every second odd number, or is it in the second one every odd number? Computationally, that's very easy to find out. You just divide the number P by 4 and you see what remainder you get. It's a very quick calculation. It's just complicated. It just goes by the number of digits in P, really. How expensive it is to divide a number by 4 is really just depends on the number of digits in the number, not the actual size of the number. So even a gigantic prime P, still has a manageable number of digits, so you can do that division really quickly. So that's just a very quick application of Euler's criterion. Gives it to you straight away. So that's good. Let's go for another one. Let's try and do 2 mod P. So 2 is typically a number you bump into when you're doing this, when you apply the algorithm using quadratic reciprocity and so on to get to the value of the Legendre symbol. Well, we could apply Euler's criterion. So it's 2 to the power of P minus 1 over 2 mod P. Now, this isn't so straightforward to analyze, okay? When it was minus 1 to the power of P minus 1 over 2, well, that was easy. Powers of minus 1 are easy to describe. Just depends whether the power is odd or even. Powers of 2 is a little bit trickier. But the argument comes from Euler's criterion. So what we do is we take this number, and what we're going to do, as it says in the notes there, we're going to get 2 descriptions of this. Get 2 descriptions of this. And by equating the 2 descriptions, we'll be able to figure out what its value is. Now, there's a little. The idea is straightforward enough. Well, the idea is easy to understand. It's maybe seeing how you might have discovered this is maybe a little bit trickier. But the key point is to get 2 descriptions of this, one of which features minus 1 to the power, or minus 1 to some power. Minus 1 to a power m. Okay. And once you get it to some power of minus 1, then you'll be able to use the approach we just used in the previous argument, that powers of minus 1 are easy enough to understand. Just depends whether the exponent is odd or even. Okay. So let's look at the argument for this in the notes. Okay. So how do we get two descriptions of that power of 2? Well, the first way we're going to do it, so we're interested in finding expressions involving 2 to the power of p minus 1 over 2. So one way we can do it is we can take all of the congruence classes, modulo p, represented by even numbers. So we're just taking all the even numbers, 2, 4, 6, 8, 10, and so on, which of course is going to end with p minus 1. P is an odd prime, remember? So we just take these numbers. Now, how many numbers are there? Well, of course, there's exactly p minus 1 over 2 numbers there. Okay, because it's half of p minus 1. So we're going to multiply them all together. Now, they're all the even numbers, so we can suck out of each one, we can suck a factor of 2 out. 2 comes out of 2, 2 comes out of 4, 2 comes out of 3. There's p minus 1 over 2 numbers there, so you're going to take out p minus 1 over 2 factors of 2. And what you're going to leave behind is 1 times 2, 1 times 2 times 3 times 4, times, lastly, p minus 1 over 2. So this number, we notice, is this power of 2, 2 to the power of p minus 1 over 2, times the factorial of p minus 1 over 2. So this is interesting because it features 2 to the power of p minus 1 over 2. And this is this number here, which we want to describe. Now, the second way we do it is we again look at these numbers, right? 2, 4, 6, 8, 10, and so on. And we're again going to multiply them. But half of them, this is, it's a really kind of odd argument. Half of them we're going to produce a different description for. Yeah. The smaller ones, 2, 4, 6, the early ones, we're going to leave alone. So 2 we're going to still represent as 2. 4 we're still going to represent as 4. 5, 6, and so on. Starting from the back of the list, the later ones, so p minus 1 is an even number, but it's also congruent to minus 1. P minus 3, which is the second last one up there, p minus 3 is an even number, but it's congruent to minus 3. So the early ones we keep as their small even representatives. The later ones we keep as their small negative odd representatives. Okay? P minus 1 is minus 1. P minus 3 is minus 3. And we do this funny thing that this alternating sign, this plus 1, minus 1, we can represent as minus 1 to the power of this indexing number here. 1, 2, 3, 4, and so on. Okay? So we're splitting this bunch of numbers here up into two groups, into the first half and the second half. Okay? First half and the second half. Now, we can't say what the middle number is going to be. The 1p minus 1 over 2, whether that is an even number or an odd number, we don't know. It depends on what p is congruent to modulo 4. P minus 1 over 2 itself could be odd or even. So but the last one in this description here is the halfway point, p minus 1 over 2. Okay. So the final element here in this list of congruences will be either p minus this, p minus 1 over 2, or p minus 1 over 2 itself. Accordingly, as p minus 1 over 2 is odd or even. Okay, so over here on the left-hand side, you see you've got all the numbers 2 to p minus 1. And over here on the right-hand side, we've got this mixture of descriptions of them. Sometimes the even number themselves, sometimes the negative small odd number. Okay, but we just multiply everything inside. So we multiply all these left-hand sides, we multiply all the right-hand sides. Now, when you multiply the left-hand sides, you again get 2 by 4 by 6 by 8 all the way up to p minus 1 over 2. When you multiply the right-hand side, some of these equations look rather funky, but they're easy to understand. When you multiply the right-hand side, what have we got here? Well, we got 1 times 2 times 3 times 4 times p minus 1 over 2. So you got p minus 1 over 2 factorial, which is good because we had that before, didn't we? We had p minus 1 over 2 factorial in our previous version. So when we're multiplying the right-hand sides here, we again get p minus 1 over 2 factorial. We also have the product of all these powers of minus 1. Yeah? You know your rules of indices like the back of your hand, don't you? When you multiply all these various powers, you have to add up the exponents. Yeah? You're multiplying different powers of minus 1. What you're doing is you're adding up all these exponents here. So we're adding up 1 plus 2 plus 3 all the way up as far as p minus 1 over 2. Now, everybody knows what that sum is, the sum of all those exponents. Well, I'm not saying you know what it is, but you recognize it as something approachable that you can deal with, because it's just 1 plus 2 plus 3. It's just the sum of the first so many positive integers. Okay? It's a very simple arithmetic sequence. There's a well-known formula for dealing with that. Okay? Okay, you don't immediately think of it as p squared minus 1 over 8, but just look. Use a green pen. 1 plus 2 plus 3. What's the formula? If you go up as far as, I'm going to choose any letter there, go up as far as m, this is, what is it? It's m over 2 times m plus 1. Isn't that the formula? Is that right? M plus 1 times m over 2. Yeah, m plus 1 is m plus 1, m minus 1 plus 2 is m plus 1. So when you pair them, they all add up to m plus 1, and there's m over 2 pairs. So that's the formula. So 1 plus 2 plus 3 all the way up as far as p minus 1 over 2, that's going to be p minus 1 over 2 divided by 2. So it's p minus 1 over 4 times p minus 1 over 2 plus 1. So what the hell's that? That's p minus 1 over 4 times p plus 1 over 2. Yeah? And that is p squared minus 1 over 8. That's my p squared minus 1 over 8 here. Okay? So, using a nice result from first year, just the sum of an arithmetic series, we get this exponent here. So now what we do is we look at what we've got on the board. Can I get them both up there? First of all, we multiplied all the numbers 2 to p minus 1. We got this description. Power of 2 times that factorial. Then we multiplied them a second time, 2 to p minus 1. We got this description. Again, the same factorial as before, and now a power of minus 1. And we know exactly what the exponent is in terms of p, and it's a power of minus 1. Those are easy to get a grip on. We should be okay. So now what we do is we equate these two descriptions. So our power of 2 times the factorial is the same as this factorial times the power of minus 1. We don't equate them, we congruence them. They're both congruent to one another. Now the p minus 1 over 2, we can strike out from both sides. Remember, you have to be careful if you're cancelling things from both sides of a congruence. You have to be a little bit careful. So you can only do it if you know it has an inverse, modulo p. You know it's co-prime to the modulus. This is a congruence modulo p. P is a prime number. The factorial is just a product of a bunch of numbers less than p. P is prime. So none of these numbers divide p. They're all co-prime to p. So the product is still co-prime to p. So this factorial can be cancelled. It does have a multiplicative inverse modulo p. Then we get this result. This power of 2 is congruent to this power of minus 1. Well, that's super duper because, super duper indeed. Why is that super duper? That is super duper because if you look at both sides of it, oh my God, I just lost it there. It is super duper because when you look at both sides of it, both sides look really nice. This power of 2, from Euler's criterion, this is the Legendre symbol that we want. Okay, so we've got what we want. The other side, -1 to some power, the other side is readily calculatable. Readily, the wrong word. It's easy to calculate. It's just a power of -1, simple. It's either +1 or -1 accordingly as the exponent is odd or even. Okay, so the Legendre symbol, 2 mod p, is this power of -1. So what's a good way of describing that? Well, the power of -1, it's gone off the page there. So we have 2 mod p is now p squared, is now -1 to the power of p squared -1 over 8. So we just need to know whether p squared. Well, because it's p squared -1 over 8, if we look at it, if we look at what p is modulo 8, we should get the answer. Okay? Remember, p is an odd prime, so there's just 4 possibilities for p modulo 8. P can either be 1, 3, 5, or 7 modulo 8. Now, if we square it, subtract 1, divide by 8, you can track through the answers. You can see that you get even, odd, odd, and even for p squared -1 over 8. So -1 is raised to this power, so -1 to that power is going to be +1, -1, -1, +1. So if we know p relative to 8, we now know what this power is, so we now know whether 2 is a quadratic residue modulo p. Knowing p modulo 8 is easy and cheap to do. You just divide it by 8 and look at the remainder. So we can now read off whether 2 is a quadratic residue or not modulo p. And finally, it's just a nice, easy tool. I mean, this looks like 4 separate cases, and it is 4 separate cases. There's 4 possibilities modulo 8 for p, but we can express them really nicely and tidily as +or -1 or +or-3. We've got +1, 7 is -1, and +3, 5 is -3. So the + or -1 gives you the even exponent. The + or -3 gives you the odd exponent. So this is how the result is normally recorded. Whether 2 is a quadratic residue modulo p, we prove now it depends on the congruence class of p modulo 8. And this is a cheap calculation to do. You just divide p by 8 and look at the remainder. So more or less immediately, just one division, you know whether 2 is a quadratic residue modulo p or not, whether 2 has a square root modulo p. And these expressions, 2 mod p is the kind of thing you run into when after you're applying loads of those properties of the Legendre symbol. So knowing its value then is key to being able to evaluate the Legendre symbol for arbitrary inputs. Okay. So that's good. Now we've still got in our focus for over the next few lectures is the law of quadratic reciprocity, which we're working towards. Okay. So we'll continue with this stuff tomorrow. Please, if you get a chance, please sit down and have a look at those arguments again. If there's anything you're unsure of about them, or if you'd like to discuss them at all, any questions about them, you can bring those to tomorrow's lecture. We can bash them out and straighten out any things in it. Okay. I shall see you tomorrow then.